The goal for this lecture is to come up with a way of integrating rational functions, that is, functions which are polynomial over polynomial. Now the way we do this is by breaking the rational functions into a sum of several simpler rational functions, each of which we already know how to integrate. So partial fraction decomposition is sort of the reversed process of adding fractions. We're going to unadd the fraction and integrate several fractions. For example, if I want to evaluate the integral of 1 over x squared minus 5x plus 6, if I happen to notice that I can rewrite this as 1 over x minus 3 minus 1 over x minus 2, then I can break this into two easy integrals. Each of these integrals is done by substitution, right? If I let u equal x minus 3, then du is dx. So that's how I'm going to do this one. For this one, I'm going to make, okay, I'm not using u anymore, I'm using v, but I'm going to let that substitution be x minus 2, then dv equals dx. And so I can rewrite the integral this way, and each of these are integrated using the log rule. And then by back substituting, I'm done. So here's the procedure. If the degree of the numerator, which is the top, is at least as big as the degree of the denominator, which is the bottom, then do polynomial long division with remainder, and then you can proceed to step 2. Next, you're going to factor the denominator completely, that is the bottom, into linear factors and irreducible quadratic factors. And as a reminder, quadratic function is irreducible if and only if the discriminant b squared minus 4ac is negative. For each factor of the form px plus q to the m, that is for each linear factor with multiplicity, our partial fraction decomposition must include these terms. That is, we're going to have a fraction for every power of the factor px plus q up to the multiplicity of that factor. And on top, we're going to have some undetermined coefficients, a1, a2, up through am, which we're going to need to solve for later. Then, for each factor of this form, each irreducible quadratic factor with multiplicity n, the partial fraction decomposition must include these terms. We have a fraction for every power of that irreducible quadratic factor up to that multiplicity. And then on top of each of these, I have a linear expression, b1x plus c1, b2x plus c2, and, well, this should be bnx plus cn. The point is that each of these fractions has some x term and some constant term, and those two coefficients will have to be solved for. Okay, and to solve for them, we're then going to clear denominators. I'll explain what that means when we do examples. And then we're going to solve for these coefficients, the a's, the b's, and the c's. And this can be done by either equating coefficients of powers of x, or else by plugging in various values of x, which cause all but one coefficient to vanish. Okay, let's see how this works in practice. Here I have a rather complicated looking rational expression, so let's see how we're going to integrate it. Since the degree of the top is 2 and the degree of the bottom is 3, I don't have to do the first step where we do polynomial long division. So I can move on to the next step, which is to factor the bottom completely. I notice that I can factor out a common factor, which is x, and then what remains is a perfect square trinomial. That's 2x plus 1 quantity squared. Okay, so that's factored completely, and our partial fraction decomposition should look like this. We have two linear factors and no quadratic factors. The multiplicity of this first linear factor, which is x, is 1. That's just x to the power 1. And so we have this term a over x. The next linear factor has multiplicity 2, so I have two terms coming from that. First with power 1, and then with power 2. And over each of those, I just have some undetermined constant, which I'm calling b and c here. Okay, well now we're going to find a, b, and c by first clearing denominators in this equation. I'm going to multiply both sides by x times 2x plus 1 squared. Then the left side will be simply this expression which is on top over here. And on the right side, what do I get? Remember, I'm multiplying by x times 2x plus 1 squared. So if I multiply a over x by that, then I just get a 2x plus 1 squared. If I multiply b over 2x plus 1 by x 2x plus 1 squared, then I have bx times 2x plus 1. And finally, if I multiply c over 2x plus 1 squared by this denominator over here, then I'm left with just cx. Okay, so now how do I find the values of a, b, and c? Just copying down that same equation here. And what I'm going to do is I'm going to plug in x equals 0 here. Then what do I get? On the left side, I just get 6. On the right side, these two terms that have x in them will be 0. And the remaining term will be 2 times 0 plus 1 squared, which is just 1 squared, which is 1. So on the right side, I do just get a, which tells me that a must equal 6. Next, if I let x equal negative 1/2, then I notice 2x plus 1 will be 0, so this term and this term will be 0. So on the right, I'll just have negative c over 2, whereas on the left, I get, well, this, 11/2 minus 16 plus 6, just by plugging in negative 1/2 to the left side. And I can solve this for c. It tells me that c equals 9. Okay, lastly, I need to find out what b is, and the way I'm going to do this is by plugging in these two known values for a and c, and also just some other random value of x that I haven't already used. How about 1? So I'm going to plug in x equals 1, a equals 6, and c equals 9 into this equation up here. So I get 22 plus 32 plus 6 on the left, and then a is 6 times, plugging in 1 for x, I get 3 squared, and then 3b plus 9, and I can solve that for b. It's equal to negative 1. Okay, and finally this tells me the partial fraction decomposition for this rational function. I'm just replacing a with 6, b with negative 1, so there's the negative sign coming from the fact that that's negative, and there's the 1, and then c equals 9. Okay, so to complete this integral, we can then focus on these three integrals separately. The first one is already one of our basic integrals, but the second two are going to require this substitution. Let u equal 2x plus 1, then du equals 2x, and so we get this. Rewriting the second and the third integrals this way, using our substitution, and then we can just evaluate. 6 natural log absolute value of x, here we have the 1/2 natural log of u, and then 9/2 u to the negative 2. You use the power rule for that one, and you pick up this extra negative sign by doing that. Okay, then we back substitute, and we're done. Okay, let's see it again. This time, we have the degree of the top is 3, and the degree of the bottom is, well, this is 2 degree 2 polynomials multiplied together, so that degree is 4. So the degree of the top is 3, the degree of the bottom is 4, which means I don't need to do polynomial long division. Okay, the next step is to factor the bottom completely. Well, from this first term I can factor out an x, leaving me with x minus 1. And this second factor, x squared plus 4, is irreducible. And the reason I know it's irreducible is its discriminant, b squared minus 4ac, is negative. In this case, it's equal to negative 16, right? b here is equal to 0, and then a and c are 1 and 4. So that's definitely negative discriminant. So each of these factors has multiplicity 1, and I have 2 linear factors and 1 irreducible quadratic factor. So for the linear factor x, I have this term, a over x. For the linear factor x minus 1, I have b over x minus 1. And then for the irreducible quadratic factor here, I have cx plus d over x squared plus 4. There aren't any repeated factors, which is why I only have one term appearing for x, only one term appearing for x minus 1, and only one term appearing for x squared plus 4. Okay, now I'm going to clear denominators in this equation so that I can start solving for a, b, c, and d. Okay, so I'm multiplying both sides by this denominator, which means that the left side will be just the numerator. And on the right side, I need to consider each term separately. If I multiply a over x by this whole denominator, I get x minus 1 times x squared plus 4. If I multiply this term by this denominator, this is what I get, and so on. Okay, so now I begin the process of trying to solve for a, b, c, and d. Last time I did this by plugging in certain values for x. In this example, I want to show how to do it more systematically. I think it would be difficult to try to find values of x which eliminate all but one variable in this case. So what I'm going to do is multiply this expression out on the right side as follows. I'm multiplying out this binomial here. Here I'm going to distribute this x to both terms, and here I'm also multiplying this x to both terms here. And then in this next step I'm going to distribute the a, and I'm going to distribute the b, and then I'm going to FOIL this out. I'm going to multiply this pair of binomials out. Okay, so in this next step I'm just going to combine like terms. I'm going to bring all terms that have x cubed in them together. All the x squared terms I'll bring together, the x terms I'll bring together, and there's only one constant term here. And now what the idea is we're going to equate coefficients of these powers of x. So I'm going to say that since I have x cubed here with coefficient 2, and x cubed here with this coefficient a plus b plus c, I must have that 2 equals a plus b plus c. And the coefficient of x squared is 0, but on the other hand, it's negative a minus c plus d, which means that 0 must equal negative a minus c plus d. And similarly for these two terms, this negative 4 must equal this expression, and negative 8 must equal this expression. So we're trying to solve this system of equations. A plus b plus c equals 2, negative a minus c plus d equals 0, and so on. These are the four equations with these four variables that we now need to solve. So how do we begin? I see the fourth equation is the simplest. I can just divide it by negative 4 and get a equals a equals 2. Okay, then if I replace a equals 2 in these last equations here, replacing a equals 2 and then rewriting, these equations become these three: b plus c equals 0, negative c plus d equals 2, 4b minus d equals negative 12. You might have to work through that to see how that happens. But this is the system of equations we have now. It's a smaller system of equations now. And so the idea is we're going to try to solve for one of these variables in terms of another, and then substitute those in the other two equations. So that we're just using the method of elimination of variables. So let's look at the first equation here. I see that means b equals negative c. So I can substitute that in to the other two equations. Right here I can replace negative c with b, so I get b plus d equals 2 rather than negative c plus d equals 2. And the second equation I'm just going to leave alone because I've already eliminated c, and so now I have two equations with the two variables b and d. And now to solve this, I'm going to simply add these two equations together because I see that if I do, that will eliminate d. On the left side I'll just have 5b, and on the right side I'll have negative 10, which if I divide by 5 I get b equals negative 2. Okay, well then because we already know that b equals negative c, we can deduce that c must equal 2. And then finally the last equation says d equals 2 plus c, so therefore since d equals 2, d must equal 4. And so our partial fraction decomposition looks like this. Plugging in a equals 2, b equals negative 2, there's the negative, c equals 2, and d equals 4. And now we're ready to integrate this function by computing these four integrals separately. Okay, the first integral is an easy one. It's just a basic log rule. The second one is almost as easy. It's going to require a substitution, but it's a rather simple one. And so we make that substitution, then use the log rule, and back substitute. Okay, the next one is also a substitution. Let v, for some reason I could have called that u, I don't know why I'm using v there, but whatever. V equals x squared plus 4, and dv equals 2x dx. Then this becomes just, here's the 2x dx, that's our dv. Oh, I've switched back to u here, that's weird. Sorry, okay, so let's call that u, and let's call that du. Alright, so now we're ready to use the log rule, and then back substitute. And I want to remark that since x squared plus 4 is always at least equal to 4 or greater, it's always certainly positive, and so these absolute value signs aren't necessary. I can just use parentheses. Okay, next, this last integral is 4 over x squared plus 4. I'm going to go ahead and do this by trigonometric substitution because I see this x squared plus 2 squared. So I'm going to let x equal 2 tangent theta, then dx will be 2 secant squared theta d theta, and x squared plus 4 will end up being 4 secant squared theta. And so if I rewrite the integral that way, I see secant squared cancels with secant squared, and 4 cancels with 4, and so I just get the integral of 2 d theta, which is quite easy. That's 2 theta plus c. And if I try to solve for theta, well, I can just take this equation, divide by 2, and then take arctangent of both sides. Okay, well, let me show how to do that integral a slightly different way, just so that you're aware that there are more ways to do this integral than one. First, I'm going to make an observation that this almost looks like the integral form which involves arctangent, except that this isn't a 1. So if I want to make that a 1, I can just divide top and bottom by 4. And this is what I get if I do that. Then, if I make the substitution u equals x over 2, then I can convert this to that integral form involving arctangent. So I'm going to let u equal x over 2, du is equal to 1/2 dx, so dx is 2 du. Then rewriting the integral looks like this. There should be an integral sign here, sorry about that. Integral of 1 over x over 2 squared plus 1, and now I'm going to do the substitution. Dx is equal to 2 du, there's the 2, and now this is just the arctangent of u, and then back substitute. Okay, so finally we can write down the full integral for this function. We had 4 different integrals. We calculated them separately. Here they are: 2 natural log absolute value of x minus 2 natural log absolute value of x minus 1, and so on. Okay, so the idea for partial fraction decomposition is first you do polynomial long division if the degree of the top is greater than or equal to the degree of the bottom. Then you factor the bottom completely, and note that a quadratic factor is irreducible if and only if the discriminant is negative. Then you're going to solve for the coefficients by equating coefficients or by plugging in various values of x, as I demonstrated here. Then you're going to integrate each partial fraction by either substitution, whether it's a u substitution or a trigonometric substitution. Usually the u substitutions will be easier in this setting. Okay, now in the next video we're going to talk about integration by tables, which I think you'll appreciate. But before we do that, please try to use the techniques from this video to evaluate this antiderivative.